Thank you very much for joining us here on the pink stage, sorry, on the pink stage. I would like to welcome our first talk in this pink stage, John Hughes. So, John, the floor is yours.
Thank you very much. Okay, so I hope you can see my slides. I'm going to talk to you about smart contract testing, and maybe I should just kick off by making sure we're all on the same page and explaining what a smart contract is. It's basically a small program that runs on a blockchain and ensures that transfers of cryptocurrency follow the terms of the contract. Smart contracts date back to the Ethereum blockchain, which was the first blockchain to support them, and that has made Ethereum the second largest cryptocurrency today. But of course, one problem with allowing programs to transfer money is that bugs in those programs can lead to money being stolen. And there's been plenty of money stolen from the Ethereum smart contracts. One of the well-known ones was the so-called DAO attack in 2016 on a crowdfunding scheme in which Ether to the value of $60 million at that time was stolen. So when you work with smart contracts, one of the things you want to ensure is that they are as little buggy as possible. Now, I'm not going to talk about testing Ethereum smart contracts. I'm going to talk about testing smart contracts on the blockchain run by these guys, a company called Input Output Hong Kong, or IOHK, who run a blockchain called Cardano and a cryptocurrency called ADA. So what is this? Well, if we look at the largest cryptocurrencies in the world, you can measure the size of a cryptocurrency by the total value of all its coins, the so-called market cap. The biggest is Bitcoin, of course. At the time that I made this slide, all Bitcoins were worth $1 trillion. And Ethereum is the second largest, worth around $1/3 of $1 trillion on that day. And on the same day, Cardano ADA was worth about $43 billion, which made them the 7th largest cryptocurrency in the world. And there are hundreds of them. So to be in the top 10 is pretty good. And since then, Cardano has gone up in value and Bitcoin and Ethereum have gone down. So today they're the 5th largest, but these things vary from day to day. Cardano is quite an interesting blockchain for several reasons. One reason is that it's the world's largest cryptocurrency blockchain that uses a proof of stake consensus protocol. You probably know that Bitcoin uses more energy than a small country to commit its transactions. And that's because the proof of work consensus protocol is so enormously expensive. Most cryptocurrencies work in the same way. So they're using enormous amounts of energy. That's been in the news recently since Elon Musk noticed it. And I would say that's clearly not sustainable in the long run. Cardano is the largest cryptocurrency that does not do that. It uses proof of stake instead. It's at least 10,000 times as energy efficient as Bitcoin from the point of view of the cost per transaction. So that's one reason why it's interesting. And that's the reason why it's gone up in value, relatively speaking, in the last month. But it's also interesting because the Cardano blockchain uses Haskell. And as a Haskell enthusiast, that makes me happy. So the entire blockchain is implemented in Haskell, and the smart contracts are implemented in Haskell. And one might hope that that would make them a little bit less susceptible to bugs. They still need testing, of course. And if you look at the Cardano documentation, you'll find that their contract language, Plutus, has a number of tutorials. And one of them is on property-based testing of Plutus contracts. And this describes the testing framework that our company built for IOHK for testing smart contracts. And that's what I'm going to tell you about today. Before I get started, I should explain a little bit more about how the Cardano blockchain works, because it's a little different from the Ethereum one. So the blockchain is essentially just a list of transactions. Every block contains a collection of transactions, and it grows constantly. Every transaction produces some outputs and consumes some inputs, which must in turn be the outputs of previous transactions. So all of the money in the blockchain is represented by unspent transaction outputs, or UTXOs they're called. Bitcoin works the same way. And in the Cardano blockchain, then an unspent output can actually contain not just ADA, but a collection of different kinds of tokens. So this is one nice thing about the Cardano blockchain, that it natively supports not only the ADA cryptocurrency, but any other tokens you like. You can coin new ones if you want. So the blockchain enforces some invariance on transactions, of course. The sum of the outputs must equal the sum of the inputs. You can't conjure money out of thin air, unless, of course, you do exactly that, which is also allowed if you forge new tokens. But the sum of the outputs must equal the sum of the inputs plus the tokens that you forge. Now, that's not the only constraint on transactions, of course. You're not allowed to spend just anybody's money. You have to spend your own, or you have to have permission to spend it. And to enforce that, every transaction output on Cardano has a verifier attached to it, which is a little function, essentially a function from transactions to Booleans. And when you submit a new transaction to the blockchain, then all of those verifiers are called, and they all get to inspect your transaction and see, does this transaction follow the rules of the contract or not? That's how smart contracts are implemented on Cardano. And forging new tokens works the same way. There's a monetary policy function that gets called to see, do you have permission to forge a new token here? Now, these functions are written in a language called Plutus, which is essentially a subset of Haskell. And so that is what is called on-chain code. It's run by the blockchain itself to check transactions. But you also need to construct transactions and submit them to the blockchain. And that's also done with Haskell code. And so a Cardano smart contract actually has two parts. There's the on-chain code in Plutus, and there's the off-chain code in Haskell, which runs in what's called a wallet. And a wallet is just an application that you run on your computer that talks to the blockchain. Okay, so how do we test these things? Well, we need to test the on-chain code and the off-chain code together. And we do that by running tests against a wallet. Every contract provides what are called contract endpoints. That's just the API of the contract. And then we use QuickCheck to test these things by generating random sequences of actions. And every action will invoke a contract endpoint that may then submit one or more transactions to the blockchain. Every transaction gets checked by running the on-chain Plutus code to make sure that it's accepted. And then we take the next action and do the same thing, and so on. And at the end of this random sequence of actions that QuickCheck has generated, we just look to see, do the wallets have the right contents? Because that's what smart contracts are all about, really. It's all, where does the money end up? Is it in the right place? Now, of course, to check the contents of the wallets, we need to know where the right place is. Where should the money end up? And to specify that, we define a model of the contract state. We call it a contract model. And for every action, we define how that changes the contract model. And then that is used to decide whether or not the final wallet contents correspond with the contract. So the framework that we've built works like this. You define a contract model, you define the effects of actions, you define the actions you want to test, and then QuickCheck will generate tests for you. When a test fails, though, because these are randomly generated, they usually contain a lot of rubbish, as well as the cause of the failure. Usually, a test fails because of just a few actions in this sequence. And the next thing that QuickCheck always does is try and identify these actions that are responsible. We call it shrinking. We try and shrink the test case to a smaller one that only does necessary things to make the test fail. And you'll see that in action in a moment. Okay, so this is the way that we've tested code with state using QuickCheck for many years. But we've built a special framework for applying it to Cardano smart contracts. Let me show you an example. It's all a bit abstract. I'm going to take a guessing game contract as an example. And this is a simple contract that IOHK provide to show you how to write Plutus code. So how does the game work? Well, the game starts when the first wallet offers some prize money. And the wallet locks this prize money, in this case 14 ADA, in a contract on the blockchain, protected by a secret password. And in this case, the password is the word secret. Okay, so once the prize has been provided, then other wallets can try to win the prize by guessing the password. So this wallet, for example, might submit a guess. This is a wrong guess. The wallet is guessing that the password is the word secret, which is not the same as secret. And when a wrong guess is submitted, then nothing happens. But if a wallet submits a correct guess, then it's allowed to ask to withdraw some or all of the prize money, and also can change the password. So after a correct guess, the guessing wallet is the one that knows the password and nobody else does. So this is the state we end up in. Okay, so that's the basic way the game works. There's just one more wrinkle to make it a little more interesting. And what we've got to do, as well as what I've described, is when the first wallet starts the game, it's got to forge a new token of a special currency whose only purpose is playing this game. And we'll call that the game token. And the point of that is to restrict who is allowed to make guesses. So before a wallet can make a guess, it must possess the game token. And that means that we can pass the game token around to give each wallet a turn in submitting a guess. So there we are. Here's the same example I showed before. It's as before, except that we pass the wallet, the game token, to the wallet that's going to make the next guess. I think the reason this is in the game is really just as an example of creating and manipulating your own currency. So I said that we test this kind of system by defining a model. Let's think, how might we model actions in this game, like making a guess, for example? Well, here's an English description of what the effect of a guess should be. Okay, so first of all, if the guessed password is correct, and if it's made by a wallet that holds the game token, and if the amount requested is less than or equal to the amount locked in the contract, then the guess should succeed. And what does that mean? Well, it means that the wallet should receive the amount requested, the password should be replaced with a new one, and the amount locked in the contract should decrease by the amount that's just been won. Otherwise, nothing should happen. So I hope that sounds like a reasonable informal description of how a guess should behave. If we look at what I've written here, though, we can see that some of the things in this informal description correspond to the contents of wallets. You know, the wallet holds the game token, the wallet receives the amount requested. And that kind of thing is something we're going to need to specify about any smart contract. The whole point of smart contracts is to regulate the flow of currency between wallets. So every model is going to need to talk about that. But there are other parts of this informal description that refer to this contract in particular. Like the guess must be correct. So we need to know what the guess is, or what the correct answer is, the amount requested and so on, the password being replaced. So those are relevant for this contract, but not for any others. And so as part of writing a test for this wallet, we need to specify these things. And we do that by defining what we call the contract model, which in this case will tell us what is the password at the moment, how much ADA is locked in the contract, and who has the game token. And then we basically just write modeling code that corresponds very closely to the description that I've given you here. I have some Haskell code here. This is the same Haskell code. I realize that if you're not a Haskell user, there are a lot of symbols. It's not necessarily terribly readable, but I just want to show you that the structure is the same as the informal description I had there. Here, look, what are we doing? It's describing how the model changes when we make a guess. And first of all, we look up in the contract state the current secret. We compare it to the guess being made. That tells us whether or not the guess is correct. That's a Boolean. We look in the contract state. We see who has the token. If it's the wallet making the guess, then holds token is true. We look at the game value, the amount of ADA, and compare that to the amount being requested. If so, enough ADA is true. And then this last bit just says that if all of those Booleans are true, then we deposit an amount into the wallet corresponding to the amount requested. We change the password to the new one, and we subtract the value from the game value. So it's very straightforward to write these models. Okay, once we've done that, then we can run tests. We call QuickCheck to generate tests, and we just supply that model in a property that I've called prop game. And if we do that, what happens? Da-da, a test fails. And QuickCheck shows us the test that failed. Here it is. It's a list of actions, as I described. And what these actions mean is that wallet number 1 tried to lock the contract, providing 0 ADA with a password 102, and then tried to lock it again with the password hello. Well, it's immediately clear that this is a stupid thing to do, right? Wallet 1 has started the game twice with 2 different passwords. Which password should you guess to get the money? Obviously, something weird is going on here. But in fact, what happens is that the contract instance crashes. And among the error messages, we find something that says we found 2 outputs and we expected 1. What's going on there? Well, actually, when we try to start the game with a lock transaction, that submits 2 transactions to the blockchain. One transaction is just paying the prize money to the contract script, and the other one is putting the contract into the locked state. And when we try and do that a second time, that second attempt to put the contract into the locked state is rejected, which leaves us with 2 payments to the contract script. And the contract code doesn't know what to do if there's more than 1 payment. It's not expecting that. So that's why this has crashed. Now, actually, when you look at this, you can imagine if you went to the contract developer and you said, if I try to start the game twice, your contract crashes. The developer is quite likely to say, well, don't do that then. So it's maybe a little bit arguable whether this is a bug or not. I tend to think this is a bug. Somebody might do this and it puts the contract into a crashed state. You don't want that to happen. Whereas the developer might say that this is not the intended usage of the contract, don't do it. So this is actually something that happens quite often when we use QuickCheck to generate random tests, because QuickCheck doesn't know what's sensible and what isn't. And so we quite often find cases that the developer might think are stupid, but that don't work right. And so if we want to continue, either we have to fix the bug or persuade the developer to fix the bug, or tell QuickCheck, don't do that. And it's important that we have a way of doing so. We do it just by specifying a precondition for the lock action. And I've chosen the precondition that there is no game token yet. So when we start a test, there is no game token. That means the precondition is true and we can perform a lock action and start the game. But once we've done that, there is a game token and the precondition is false. And that means that QuickCheck will not generate any more lock actions. So once I supply this precondition, I won't show you the code for that, it's easy, then QuickCheck will no longer generate that test case that failed. What happens next? Well, now we can run tests again. And what do you know? They still fail. Okay, let me just remark here, this failure needed 10 tests to find, 10 random tests, and 6 shrinks. So this test case that we're seeing here, it has been shrunk. The first random test was much harder to debug than this, but this test case shows us exactly what went wrong. And what's going on here? So first of all, wallet 2 is starting the game and specifying hello as the password. And then wallet 1 is making a guess. And it's guessing hello. So it's making a correct guess. But it crashed. And if we read the error messages again, we'll find one of them says insufficient funds. Well, you might wonder, why do you need funds to make a guess? Right? Remember that game token? You have to have the game token before you're allowed to make a guess. Does wallet 1 have the game token in this test? No, it was created by wallet 2 in the first step, and it hasn't moved since then. So that's why this test fails. And once again, I would say this is an error, that the contract ought not to crash, it ought to behave cleanly if you try and make a guess without holding the game token. But you might also say, don't do that. And so, of course, we can add a precondition, again, that tells QuickCheck, don't do that. And then we can go back and run tests again. And actually, there are more problems that emerge. But if we keep doing this, what happens is that we end up finding out what exactly are the preconditions that are needed to make the contract work. And there's one more precondition, and then then everything runs fine. So that's comforting. But we realized when we sat down and thought about it that this kind of testing is not enough for a smart contract. Why? What we're doing essentially is we're making a random walk in the state space of the contract, and we're testing that nothing bad happens. Nothing goes wrong. Nobody steals your money. And of course, that's important to test. But it isn't the only thing you care about when you write a smart contract. When you write a smart contract, you also, we believe, have some kind of goal state in mind. And typically a goal state might be one in which no money remains locked in the contract. And you want to know not only that nothing goes wrong as you run your random tests, but also that there's always a way to reach that goal state. Look at it this way. It may be that you put some money into a contract and people are calling their API and nobody can ever steal your money. That will be a small comfort if you can't recover it yourself. So this is what we want to test. We want to test that you can always reach the goal state somehow. But if you think about it, this yellow sequence of actions that I've specified here, or drawn here, that's very different in nature from the blue sequence. We can't generate those at random because a random sequence is very unlikely just to happen to end up in a goal state. And what if we generate a random test and it doesn't end up in a goal state? Well, so what? Who cares? All that says is you're not always in a goal state. So that doesn't test the property we want to test, which is that something good is always possible. So that yellow sequence, it needs to be constructed carefully so that it reaches a goal state. And a random sequence won't do it. It's very difficult to see how to find that yellow sequence automatically. And the approach that we take with QuickCheck when something is difficult to do automatically is to make the user do it. So this is what we want to do. We want to allow users to specify a strategy for reaching the goal state, and then we will test with QuickCheck that that strategy always works. Let me show you what that looks like with a game contract. Here is how I might try to specify the goal. Okay, so this is a little bit of test code in Haskell. I've called it no locked funds because that's what we're going to check. And what it says is that after any sequence of actions at all, there should be no money locked in contracts. And of course, this isn't true as it stands. I've specified the goal, but I've not provided any strategy for reaching it. And if I take this and I give it to QuickCheck and run tests, then QuickCheck will, of course, find a failure. And in this case, here it is. We can see what the failures look like. If you look at the two red lines, the first one is what the test has done. And wallet 1 has started the game with this password, and it's locked 1 ADA. And then the assertion fails because the locked funds are not 0. Well, of course they're not. We've just locked 1 ADA. So that just shows what a failure looks like. So now what I need to do is to specify my strategy for recovering the money from the contract. And I can do that just by extending this test. So I add these lines in black here. What do they say? Well, first of all, I'll just pick any wallet from the set of wallets. And that's the wallet that is going to recover the money. And then I'm going to do so by making a correct guess, of course. So the next two lines view the contract state and extract the current value of the secret and the current game value. And then I'm just going to make a guess with the correct values, and that should result in the locked funds being 0. Okay, does it? Well, we just run QuickCheck to find out. Generate tests. Ta-da, here we are. Oh, it's not true. It's not true. We've got a bad precondition error. And if we look at what happened, the only thing we did was this witness line. And witness corresponds to the choices that can appear in a strategy. So this means we chose wallet 1 to be the wallet to recover the money. And then we wanted to make a guess, but we couldn't because the precondition was not satisfied. That's why it says bad precondition. Okay, what is the precondition for making a guess? Well, I showed it to you a few slides ago. Here it is. The wallet holds the game token. Look at this test. Does wallet 1 hold the game token? No, of course not. We haven't even started the game. There is no game token. So, of course, the strategy doesn't work in this case. And that just reminds us that when we say the strategy has to work after any sequence of actions, it really has to work after any sequence at all, including the empty sequence. So, okay, so there's a slight mistake there. Let's fix it. So, of course, the annoying thing here is that before we start the game, there is no money locked in the contract. So we're in the gold state already. There was no need to do anything at all. And so let me just refine my strategy a little bit to say, well, if I don't need to recover anything, I won't do anything. Here we are. That's the red line that I've added to the strategy that just says, I'm only going to make a guess when the value to be recovered is greater than 0. So you can see that I can develop the strategy bit by bit in a kind of test-driven manner, which I think is really nice. Okay, so does this work now? Of course not. Still fails. Here's the new failure. And what we see happening here is, first of all, wallet 1 locked 1 ADA. So it started the game and locked 1 ADA. And then we chose wallet 2 to recover the money. And we tried to make a guess. Wallet 2 tried to make a guess. And there was a bad precondition. Remember the precondition of guess? You have to have the game token. Does wallet 2 have the game token? No, wallet 1 has it for the same reason as before, because wallet 1 minted the game token when it started the game, and we have not given the token to wallet 2. So that's a very small error. To fix it, I have to give the token to wallet 2. So that has to be a part of my strategy. And there it is. That's how I add that line. And now the strategy works. And if I call QuickCheck, it will generate and run 100 tests by default. I would usually run 10,000 tests at this point, just to convince myself that the strategy really does work. Now, of course, this is a very simple example. And I'm sure it's not a surprise to you that this is how you can get the money out of the contract. And this is our point, really. We believe that developers know how you should be able to get the money out of their contract. But we see value in writing that strategy down, because while developers think they know how to get the money out, it's easy to forget a corner case. In this case, I forgot you have to give the token to the contract first. Or it's maybe easy to forget some tricky case in which it doesn't quite work. And those are the kinds of cases that can leave you with money locked and inaccessible in your contract. So we see value in writing the strategy down and testing that it always works. This little strategy language, by the way, there's a lot more to it than I've had a chance to show you today. You can, for example, mix random actions and strategy actions. You can make random choices in the strategy. You can apply weights to random choices and so on. And I'm very excited about this work. It's been fun to work with testing smart contracts, of course. It's an interesting domain. But not only that, it's led us to think of this new kind of property, new kind of test we want to perform that lets us apply property-based testing not only to safety properties, the kinds of things we've done for a long time, that test that nothing bad ever happens, but also liveness properties that test that something good is always possible. And this, I think, is an exciting new development in property-based testing in general that I expect to be useful in many other situations too. Okay, and those were the slides that I had for you. So I'm ready to take questions.
Hey, thank you very much for your wonderful presentation. Before we are going to the questions, I would like to ask the audience that they can use the chat function or the Q&A section to type their questions in. And I would like to present you your small gift from the conference. So I hope you recognize yourself there. It's a little bit of the fun picture of you, and this will be shipped to your address. So
Okay.
hope you will enjoy coffee or tea from it as you like.
I will look forward to that.
Okay, so until we are getting to the questions, there has been nothing arriving yet, but I have one question. Actually, in the very beginning, you mentioned that there is a huge energy consumption when it comes to this cryptocurrencies and when it comes to this ledger technologies. Is there any projects? Are you aware of any projects of reducing this footprint? Is it something that is already boiling? I guess they started to work with it.
Yes. So I think everybody realizes that it's a problem, and there are a variety of approaches to addressing the problem. There are ideas that retain proof of work but move many of the transactions off chain, for example. So there's things called side chains, part of whose purpose is to reduce the energy consumption. But I think that doing away with proof of work altogether and using proof of stake instead is probably the most radical and complete approach to avoiding this energy problem. So you might say, I think IOHK are betting on proof of stake winning out in the long run. The Ethereum blockchain, for example, has been planning to move to proof of stake for quite a long time, and I understand it's going to happen real soon now. It's been going to happen real soon now for a while. So it seems to be not quite as easy as you might hope, but I imagine that has to be the way that the sector moves in the long run.
I see. Thank you very much. Another question, maybe. I'm working with IoT solutions in my company, and I was just wondering, how much do you think this blockchain type of security would be applicable to IoT solutions, like devices being secured by this blockchain technology? Do you see any applications on that field, or that you know of?
So what a blockchain lets you do is to record a trusted sequence of transactions without necessarily trusting any participant. So if you've got an application using IoT devices where you want to keep trusted logs of events or whatever, then I guess you could use a blockchain for doing so. I think you wouldn't want to be running mining operations, for example, on IoT devices, just because their energy really is at a premium.
Okay, thank you very much, and thank you very much for the answers. Actually, I don't see any question at the moment, so I would like to ask the audience that this is your last chance to put the question. Not the last, by the way. This is your last chance during this presentation, but during the conference, social events, and even after, I guess, John, they can contact you, right, for the different questions and the different inquiries. Just one last question from my side is for the fun fact. From where are you calling in?
Oh, I'm in Gothenburg, in Sweden.
In Gothenburg, okay.
Yes,
nice
working
city.
at home. Very nice city.
Nice
yes.
City. Okay, thank you very much. Thank you for your talk, and thank you for listening as well.